Welcome back to linear algebra. In this video, we're going to be discussing the idea of a change of basis. As we've seen previously, for any vector space, there are any number of different sets which will form a basis for that vector space. And using any basis for a vector space, you are able to find a unique representation of any given vector in the vector space. So our goal here is to look at the representation of a vector under one basis and try to find a relatively straightforward way of turning that into a representation of that vector under a different basis without having to go through the trouble of looking up what the basis actually represents, calculating what that vector is in the vector space under the standard basis using the basis that you have, and then trying to find the transformation to get that into the new basis, which is a system of equations that needs to be solved and generally will be a lot of fun. So if we can shortcut all of that, then we're going to be in pretty good shape. Luckily, it turns out to not be that difficult to do so. So let me get my head out of the way. Let's formalize those ideas and see where we can go from there. So let's let V be an n-dimensional vector space. Let's take set B, which has n vectors, B1, B2 through to Bn. And let's take set U, which is also going to have n vectors, U1, U2 through to Un. Both be a basis for V. We know that a basis allows us for any vector in the vector space, we can write that vector represented relative to basis B with an ordered n-tuple, C1 through to Cn. We can also write that vector V relative to basis U using a different ordered n-tuple. Let's call it K1 through to Kn. And of course, we know that the purpose of these ordered n-tuples is that we can write V is C1b1 plus C2b2. So that's the purpose of the ordered n-tuples. And again, our goal is to find a way given C1, C2 through to En, calculate what we will get as K1, K2 through to Kn without needing these linear combinations. Right? Because again, we have that option. Given C1 through to Cn, we know what basis B looks like. We can calculate that linear combination and get a direct representation of vector V. And then given the direct representation of vector V, we can set it equal to the linear combination involving the u's. And generally speaking, we will find a way to set that up as a system of equations and solve the system of equations, and that will give us the representation. It absolutely will always work, but it's going to involve solving a system of equations every single time. And we'd really like to avoid that for what I hope are obvious reasons. We'd really like to not have to go through and deal with all of that time. And there are a couple of different ways that you can think about why and how we are going to go about this. The most direct one we have ordered n tuples of real numbers. And given an ordered n tuple of real numbers, we can treat it as though it was a column vector in the Euclidean vector space Rn. And by knowing that, we can rephrase this question as looking for a linear transformation which maps, let's shorthand that now, the C1 through to Cn is vector V in terms of basis B, and we want to map that to vector V in terms of basis U. And we know how to write a linear transformation. If we know what the transformation we are looking for does to the Euclidean basis vectors, we can write out what our transformation looks like as a matrix, and then use that matrix to calculate the transformation for any of these vectors. So that changes our question. What vectors in our vector space under basis B have the representations that look like the standard Euclidean basis vectors. Well, that's the representation under basis B of the vectors in that basis. So this is B1. Represented under basis B. This is B2 represented under B, and this is going to be Bn represented under B. Knowing that, we have a nice way of figuring out where these things are going to transform to. Because we want the transformation to take each of these vectors to the corresponding thing represented under basis U. So we want B1 under basis B to transform to B1 under basis U. We want B2 under basis B to transform to B2 under basis U. And we want Bn under basis B to transform into Bn under basis U. Once we have managed to do that, we know that we can write the transformation, which I'm going to write as P subscript B to U, as a matrix where the columns are exactly these results. B1 under U, B2 under U, Bn under U.